lecture of Professor Aparna Baskaran on Foundations of Non-Equilibrium Statistical Mechanics, Active Meta Edition. Thank you very much.
I will tell you nice stories starting tomorrow. Today is the last, let's do math and so on. This microphone has chiral symmetry. It goes on only one way. Okay. All right, shall we get started? Okay, so let's begin what we're talking about today. So this is the plan for today's lecture. I'll start with a bit more philosophizing like we did last time. Then we'll look at a story so far in terms of what is the math journey that you and I have taken together over the first lecture. Then we'll launch into the first topic, which is the Langevin description of self-propelled particles. I'm not going to cover any new ground. You have already seen all of this stuff in Ricardo's lectures, Rodrigo's lectures. And therefore, what I will be doing will be making you do it, do the math. We're not discretizing anything. We're actually going to solve the Langevin equation, okay? Then we'll come back to me. I will talk about the thermodynamics of an ideal gas. And then, if time permits, I have one more fun exercise that's a lot less math and a lot more Googling. So let's see how far we get today. And let's get started. When I was philosophizing yesterday, I was trying to motivate active matter in the broadest context possible. And I said that by laundry listing the properties of life, I don't know how to define it as one quantity, but I can define it as several attributes, such as homeostasis, organization, response, and stuff like that. It gives us a handle on trying to understand how life comes out of matter. That's the game that we are all playing. And at the moment, we're playing the game as in how do particular properties come out of matter, right? And then we build up from there to try to see if I can get an entire organism out of it. For today's edition, I noticed that when Francesco was asking you guys, are there any non-physicists in the room? Nobody stepped up. So you all identify as physicists. That was my interpretation. So today's philosophizing is from the perspective of we are all physicists here and we're better than the other humans out the door. So our game is let's understand nature. And nature ranges from, if I'm thinking of quarks and gluons, fundamental forces and particles, or I could be thinking of materials of every kind, living or dead, that's all of us in this room. Stars and galaxies, if I'm an astrophysicist, the whole universe, if I'm a cosmologist, right? And what's happening across all of these scales is that nature speaks math. What do I mean by that? I mean that the only way we learn anything about nature is through measurement. And the only way we understand anything about nature is through math, through writing down complete and rigorous mathematical theories. In this context, the mathematicians and the philosophers are grammarians. They tell us the rules of the language and the possibilities of the language and things like that. We are the prophets. We are the people who understand the math and the measurement. We bring it together into a nice story in some other natural language, English or Portuguese or whatever, and then we share it with the world. So we are the prophets, then we should spend all our time praying so that God can speak to us, right? That means we should spend all our time doing the math. When you're looking at data, when you're looking at statements that are based on empirical observations, always drill down to the data to see how that observation was inferred from whatever raw data they started with. And similarly, when somebody makes a claim based on a theoretical analysis, based on a model, based on a mathematical calculation, always drill down to what it is that they did. before you decide to believe whatever English story somebody is selling. Okay? So given all of that context, let's look at the story so far. What did we do in the first hour and a half of trauma together? We talked about the mathematical language of non-equilibrium statistical mechanics, and I mentioned that it's the language that allows us to bridge across scales. It allows us to bridge information that we obtain using very fine clocks and rulers, nanosecond clocks and angstrom rulers, to information that we obtain using more macroscopic rulers, like micron-sized rulers and microsecond clocks, right? And the bridge building has taken several different forms. Thermodynamics and hydrodynamics have been derived using kinetic theory. Heat, work, entropy production have all been reconciled using stochastic thermodynamics. But these are technically slightly more sophisticated than we can do in the course of 1.5 lectures. So what we chose to do in the last class was to focus on diffusion as the particular macroscopic process and do all of the math to get to all of the story that we already know about diffusion. So in the context of diffusion, I mentioned 2 processes that are representative of diffusion. One is just plain diffusion. You put a drop of ink in water, it spreads. The other is damping. And I mentioned that both of them arise because of the fluctuations of the water molecule. I want to sharpen that statement a little bit today by noting that in the process of diffusion, the fluctuations are at the level of one particle. The fluctuations that you observe at the level of one particle is what gives rise to Brownian motion. And those fluctuations arise because of the absence of knowledge of the many particle system, which is the water. Does this make sense? So the fluctuation comes at the level of a single particle, and then when you take many of these single particles that are fluctuating, dissipation appears on a much longer length scale. You get irreversibility and some phenomenon where you can tell the direction of time when you measure over much longer length scales. On the other hand, when you consider damping, the fluctuations is at the level of the many particle system. The many particle system, namely the water, is in an equilibrium state, and you're looking at fluctuations about equilibrium. Right? So it is an absence of short time scale information that appears as fluctuation when you're looking at it at the level of your colloidal particle. But the dissipation appears at the level of the colloidal particle. So your macroscopic system here is actually the colloidal particle when you think about it as damping. Right? All of this is just game playing. I, at the end of the day, have Newton's equations for everybody, for my colloidal particle, for all my water molecules and everything else. But by partitioning the math cleverly in terms of fluctuations and dissipation, we can build the framework that will allow us to characterize what these systems do. Okay? Now, what did we do yesterday? We talked about the Langevin equation, and I mentioned that we are partitioning the Langevin equation into 2 terms. The net force exerted by the water on my Brownian particle is partitioned into the friction force, which is the damping force I expect due to the fluctuations of water about the equilibrium state, and then a stochastic force, which is over and beyond what I can estimate by equilibrium fluctuations of water. Right? And so I use this partitioning and in the process, we talked about stochastic processes. I tried to tell you what do I mean by Gaussian white noise. And I casually, without paying any attention to it, introduced path integrals without ever talking about it. Path integrals are a very powerful technique to solve stochastic problems, but of course we'll conveniently not talk about it. That was just a teaser. And what we did in terms of calculations was we said, okay, I only need to know 2 things. The noise is Gaussian, so it only has 2 cumulants. The 2 cumulants are given by the expression on this slide. And using just this information, we did some calculations using the Langevin equation. Everybody with me so far? Okay. Now, Gaussian Markov process, sorry. What are the things we calculated? We calculated the RMS for the speed, right? We calculated V square of t averaged over the noise. And what we did after we calculated the expression for V square of t is we imposed post hoc a condition on my system saying that at long enough times, the mean square of the velocity should be indistinguishable from the temperature of water, right? I put that condition in post hoc, and when I put that condition into the problem post hoc, what I find is that the fluctuation and the dissipation have to be related to each other, and the proportionality constant is called the temperature. Yes? Is this ringing bells? Are there better ways of saying what I'm saying? Okay, I'm sensing some general unhappiness that might have been got to do with too much fun outside of the lecture, but let's go on. The other thing that I did was I flashed at you a calculation that will allow you to calculate mean square displacement from the same kind of approach. And the mean square displacement turns out to be 2 kBt by friction constant going linearly in time at long times. This allows me to recognize the diffusion coefficient. kBt by friction is the diffusion coefficient because 2 dt is what I would have written down if I thought about it as a random walk. Yes? Okay. Now, in the material that's posted on the website for our school, there is some additional reading that I did not talk about in my lecture. So I want to spend a couple of minutes just orienting you to that reading because it's a really cute problem and it's helpful everywhere. Once you can do this calculation, there's all kinds of non-equilibrium StatMech games that open up to you in all kinds of fields. So I want to talk about it for a minute. What the reading addresses is where does the Langevin equation come from? As I mentioned a moment ago, what is truly happening is I have some Newton's equations for my colloid and my water and everybody else. So I just have lots and lots of Newton's equations that are evolving in time, right? So if this Langevin equation is indeed an emergent description, which only arises because my clock and ruler cannot resolve the Newton's equations, then I should be able to derive the Langevin equation from a Newton's equation. There are many ways of doing it. Some are more technically sophisticated than others. The one that presented in the reading is a particular way that I like a lot. And that way is to start with Newton's equations associated with a particular Hamiltonian. So let's all stare at this Hamiltonian for a moment. Does it look like a harmonic oscillator? How about now? Does it look like a harmonic oscillator? Okay. So all I have is apparently one free particle with momentum p naught and a bunch of harmonic oscillators with momentums pj and positions qj, right? When I unhide this, all that's happening is the particle that is called with the name 0 is harmonically coupled to every other particle in the system. So this is an example of a particle interacting with a harmonic path. Okay? This particular Hamiltonian has been in the literature for many, many years now and actually forms the basis for all of non-equilibrium statistical mechanics that is known in the context of quantum mechanics. If you talk to actual people who work on quantum quenches and equilibration and things like that, they will claim they know more than the Caldera-Leggett theory can predict, but they don't. Because all of those calculations are very approximate and there's so much cheating going on in the math that it will take us a few years to know what they know, right? But this Caldera-Leggett Hamiltonian is a very beautiful Hamiltonian. And as we all know from StatMech classes that we have taken in our lives, that the harmonic oscillator is the only problem physicists know how to solve, right? You can always do all of the integrals. If it's quantum mechanics, you can solve the eigenvalue problem. It's the one problem we all can solve, right? So it's a very nice system in which to derive the Langevin equation. And I will sketch really, really quickly what is in the notes. But the sketch is just to motivate you to spend some time with the notes because this Caldera-Leggett Hamiltonian is very useful. It's a very nice toolbox in which to explore ideas about non-equilibrium statistical mechanics. And if you just Google it a little bit, you will see that this Hamiltonian appears everywhere. For everything that people want to demonstrate in non-equilibrium statistical mechanics through an exact calculation, this Hamiltonian will show up. What happens in the notes is I start with the Newton's equations for my n+1 particles. If you will notice, I have a particular particle that I'm calling 0. These are the equations of motion for that particle. And then I have a whole bunch of particles that are labeled by j. These are the equations of motion for those guys. Okay? Some mathematical rewriting. Nothing actually happens. You just rewrite the equations lots of different ways. And you end up with an equation for the particle that you're interested in, the one that's called 0, that looks like this. where I've successfully massaged my equations to make them look already Langevin-like. Can you see that it looks Langevin-like? There's something that's proportional to the velocity. It's non-local in time, but it's still proportional to the velocity. So maybe I can switch to the blackboard for just a quick minute. Let's look at that equation. Now, this guy plays the role of a friction constant, but that friction constant depends on time. And it is multiplied by the momentum, which is just the velocity. Friction times velocity is how the friction force looks, but there is a retardation in the velocity that it is multiplying. So this basically the analogy that you should look at is this is like saying dou T P naught is equal to minus friction constant times P naught plus some fluctuation force Fp. Only this guy gets fancier. And once you write down this fancy version, you can also prove that just by demanding that all of the bath particles be in thermal equilibrium, you can prove that the noise correlations in your system have to be proportional to the friction kernel K. This is the generalized fluctuation dissipation theorem, where I don't have to make stupid approximations of Markov processes and delta functions in noises and things like that, which are all truly unphysical anyway. I can prove it in a much general context. So I encourage you to waste an hour of your life working through that part of the notes, because it'll give you some superpowers when you're reading the literature. Once you see the Caldera-Leggett Hamiltonian and see its calculations, a lot of things in the literature start making sense. Okay, that's just my advertisement for my favorite model. Now, where did we stop last time? Where we stopped was we started with the Langevin equation, and we did a whole bunch of mathemagic, so to speak, because I didn't give you enough time to actually see the tricks that were at play to derive a Fokker-Planck equation. Okay? And what I want to do today is I want to pretend that the horror of deriving the Fokker-Planck equation never happened and just work with the Fokker-Planck equation. Okay? So we're going to work with the Fokker-Planck equation for a couple of minutes. And what I want to do is I want to take the Fokker-Planck equation and ask you to do a little bit of work to get to the diffusion equation. Is everybody clear on my objective? I wanted to start with the Langevin equation and get to the diffusion equation. That was my original goal. But we stopped when I got to the Fokker-Planck equation. So now let's get to the diffusion equation. To get to the diffusion equation, let's start here. Let's start with some definitions. The concentration field is defined as the integral over velocity of the full distribution, which makes sense. If you integrate out the velocities, what should be left should be the concentration of the particles. And I define a current J, which is the first moment with respect to velocity of my probability distribution function. Now, everybody take a piece of paper, take pens, and make an effort to take the Fokker-Planck equation that is there on the slide here, and take moments, integrate V out, and, oh no, that's not what I was supposed to do. And integrate dV, multiply by V and integrate with dV. Take a minute. Because of my crappy animation, I already reviewed the first part of the answer. There should be some writing. Take the Fokker-Planck equation that is there on the slide, integrate the velocity out. I did it. That's awesome. here. I'm looking for a long white chalk that will make me happy. As I keep saying over and over again, watching somebody else do math is like watching somebody else ride a bike. You have to get on the bike for it to make sense. Do you agree with what I have on the board? When I integrate over the velocity, I get this from the first term by the definition of J, and these two terms vanish. I am unhappy with what you're saying because, yes, ma'am. Why this goes to 0? Okay, so let's start here. Let's do integral dv, C over m, dou by dou v, vf, which is integrate by parts minus integral dv. Minus vf c over m evaluated at the surface. Is this okay? This is a total derivative because I'm integrating with respect to v. Fundamental theorem of calculus, move it on the other side, you get a term that is evaluated on the surface. And we are StatMech people here. Our systems are extensive and we don't care about surfaces. This is 0. Everything goes to 0 at infinity for us. Right? This integral goes from minus infinity to infinity in 1D. And everything has to go to 0 at infinity because we are dealing with the physical systems. The probability distribution is integrable. Nothing funny can happen at infinity except stuff can vanish. Does that help? Okay. Now, given this statement, can you see why this term will be 0? Again, there will be a surface term that will be dou f by dou v evaluated on the surface. And if you have an integrable function, this thing also vanishes at plus and minus infinity. These are all the kind of things that you want to be aware of, because when we go to active matter, surfaces rule the world. Whenever you start with a theory where somehow, somewhere in some previous step, somebody dropped an integral because it vanishes at the surface, the theory will not work at active matter. So you want to be aware of what are the steps and what are the assumptions so that when you go to new physics, you're aware that, oh, maybe the surface term is not vanishing. Maybe I have to go back and do the calculation again. Okay. So is everybody okay with my first equation? Okay. Now the second equation, which would be this guy. Now all you have to do is do the same integration by parts on these terms, but you have a v here. Yeah? When you integrate by parts, it will hit the v. It won't become a surface term. So can I maybe do one term again? So if I do integral minus infinity dv, friction over mass, dou by dou. Sorry. Did something funny happen here? Is everybody okay with this? I integrated by parts, so I got a minus sign, and I got that. And my definition of integral dv vf, according to the second equation on that slide, is this guy. So when I multiply by the velocity and integrate, and integrate by parts and assume that surface terms don't vanish. I mean, surface terms do vanish. Sorry, my active matter brain turned on suddenly. You end up with this equation. So what did we do so far? We took the Fokker-Planck equation and took the first two moments with respect to the velocity of the Fokker-Planck equation, okay? And ended up with the two equations on the bottom of my slide. Okay, let's assume that's all right. Now I want to look at the second equation. This is also crappily animated. The answer came up before it's supposed to come up. But let's for a moment, so far we did math, right? So far we didn't do any physics. We started with an equation, we did a bunch of integrals and ended up in another equation. Now let's turn on our physics brains and discuss length scales and time scales for a minute. Now, if I look at that equation that I have for J, let me write it over here. Yes? Okay. Now, I don't know what F is, and I don't want to solve the Fokker-Planck equation. So I want to wear my physicist hat and reason my way to some approximation. Okay? This is the only thing English is good for, namely when you're trying to make approximations, right? Otherwise, you should just focus on the math. It becomes symbolic manipulation at that stage. But now let's reason our way to where I want to go. Let's ask, I know the Langevin equation, right? I know the Langevin equation is of this form. Yeah? If I ask, what sets the time scale of the positions, change in position of particles, would you agree with me that it would be the average velocity of these particles? Is that okay? The position changes on the time scale of average velocity. And the average velocity is approximately this. Is that reasonable? Because I am in equilibrium with a bath at temperature T, so the positions are going to relax on a time scale that is set by this guy. Okay? To convert this into a time scale, I need a length. I don't know what length to use right now, so the time scale will depend on what length I'm looking at. Okay? So if I want to convert this into a time, wait, this is V over T, VL over T, so I want to bring this to the denominator of an L. So I have some length scale I don't know, and square root of kBt by m. Yes? That's the time scale over which the positions of these guys are going to change. And you have to, that time scale will set by what length do you care about? Do you care about the position changing on the length scale of the particle size, or do you care about the length scale changing on the position of some coarser ruler? We are looking for diffusion. We don't care about the position changing on the size of the particle. We care about the ink expanding, right? I don't care about how much one molecule moves. So my length scale is actually much larger, right? So this time scale can be a long time scale depending on the length. Now let's ask, what time scale does the velocity change on? Would you agree with me that the time scale on which the velocity changes is this guy? That's the exponential that's going to sit everywhere when I solve that equation, right? So the velocity is going to change on that time scale. Now, I have no control over this time scale. This is set by the viscosity of my system, the mass of my particle, the size of my particle, and things like that. But this length scale, I have control over. This is set by what ruler I'm using. And I'm not using a ruler where I can resolve individual molecules of ink. I'm using a ruler where I'm watching the droplet spread. So there always exists a length at which this time becomes much longer than this time. Let's call this TV and let's call this TX. TV becomes much longer than TX. Yes?
It's the other way around, right? TX and TV, or?
Oh, yes, sorry. Yes, yes. Is everybody buying my physics argument so far? Now, supposing you can find a circumstance under which this approximation is true, then under these circumstances, it's reasonable to assume that f of x vt becomes the equilibrium distribution for the velocity and some concentration field that is still changing as a function of time. The positions have not relaxed, but the velocities have relaxed to equilibrium already. This is the standard game one plays when one is doing non-equilibrium statistical mechanics. One decides what is the clock and ruler one is using to carry out one's measurement. And when my ruler is such that this time scale becomes much shorter than this time scale, this is a good approximation. Now, if I use this approximation in here, I can do this integral, right? Because it's F equilibrium is Maxwell-Boltzmann. I can calculate V square of a Maxwell-Boltzmann. And even if I can't, Mathematica can, so I just ask Wolfram. Is this okay? So now let's just use this approximation in this expression. Then I will get some kBt that comes from here and one derivative with respect to x of the concentration field. So let's write that down. Yes? Sorry.
Should be Tx should be the time characteristic time for the velocity equation. No?
Oh,
Yeah.
you're saying I have the notation wrong. Yes.
Yes.
Yes, yes, absolutely. I'm
That's what I
being
meant.
very stupid. I'm having brain farts. Is this, yes, that is typo. There is a very subtle distinction between typo and stupidity. So you just have to believe me that it's a typo. So yeah, so yes. So the time for the relaxation of your spatial positions is set by your ruler, and this is the one that's going to be slow. And the time scale for the relaxation of the velocity is determined by some microscopic parameters that I can't control. It's not a choice of ruler or anything. It's set by the mass of the particle, the velocity, viscosity of my fluid, and things like that. Right? So I choose a ruler so that this happens. When this happens, when the position is relaxing much more slowly compared to the velocity, this is a good approximation. You can assume that the joint distribution function becomes a product of distribution functions where the velocity has already relaxed to equilibrium. Now I make this approximation and substitute it in here. What shall I erase? I'll erase this. This equation becomes dou Tj is equal to minus C over Mj minus kBt over M dou by dou x of C of x comma t. Is this okay? Let's stare at the steps for just a minute. We started with the Fokker-Planck equation. We took moments of the Fokker-Planck equation to try to identify what equation governs the concentration. The diffusion equation is something that is associated with the concentration, right? And once I calculate the moments, I find two equations, one for the concentration and one for the J. Maybe I should write the concentration equation here as well. Yes? And then I used some physics reasoning to cook up an approximation for this term that I don't know how to calculate. And And my physics reasoning was scale separation. There is a scale separation in time between the relaxation of position and the relaxation of velocity. So the velocity can be approximated by the equilibrium distribution. And when I make this approximation, I end up with this equation. Okay? Now, one final approximation, but this was consistent with the approximation we made here. We already said that I'm going to use a clock where I'm resolving Tx, but I cannot resolve Tv. Right? My clock can only measure milliseconds or microseconds or something, while TV relaxes on some nanosecond time scale. So this is basically 0. So if this is basically 0, this is not actually changing as a function of time, because this exponential would have killed it. Do you see what I'm saying? The same microscopic time scale is showing up here. So it is reasonable to set this equal to 0 and say that J is equal to kBt by m. No, the m's cancels, so I get kBt by friction, dou by dou x c. Yes, you did not understand why I was allowed to do this. Okay, so let's try to do that a little more slowly. So let's solve this equation. If I solve this equation, the solution would be j of x comma t is equal to e to the minus c over mt j of x comma 0 minus kBt by m integral 0 to t dt prime e to the minus c over m t minus t prime dou by dou x of c of x comma t prime. Is this okay? This is just a solution of that equation. I haven't made any approximation yet. Yes?
What happened with the f of v in the equilibrium? It must...
Oh, I just did the integral. Oh, okay. So what I did was I substituted this in here, and I said integral dv v square e to the minus v square mv square by kBt c of x comma t. Right? That's what this integral becomes when I substitute this guy in here. Okay. And then I just did that integral.
Okay. Mm-hmm.
Is that all right? Other comments before I address the question associated with why I was allowed to set dou tj equal to 0? Now, this integral is only going to matter if my clock can resolve the time over which this exponential is changing. This exponential is set by the time constant m by c, which is basically 0 on my clock. Does this make sense? M by c is a nanosecond time scale. My clock is a microsecond clock. That's basically 0. So the moment I start looking, it has already gone to 0. Right? So this, you have to take the limit where this guy, this time scale, goes to 0. And when you take the limit when this time scale goes to 0, what you will find for this expression is j of x comma t is approximately equal to kBt by m dou by dou x c of x comma t. This guy becomes a delta function, and this just gets evaluated at the value. You have to do a little bit of asymptotics to do this step, but make a note of the step. And then you ask Google how to do asymptotics on this. And Mathematica knows how to do asymptotics on this. You ask Mathematica to figure out how to take the limit, m by c going to 0. Mathematica can take the limit for you. Okay? I don't want to build asymptotics. Everybody knows Taylor expansions, but almost nobody learns asymptotics. So it takes half an hour to build it. Did I kind of sort of answer your question? I didn't really, because I skipped a couple of steps. But that's roughly what I'm saying. I'm saying that this time is so large that I can drop this and just set that equal to 0. Now, do I have the diffusion equation? I have Fick's law, right? Current is equal to gradient in concentration. Is this what you guys know as Fick's law? Now, if I substitute Fick's law back into this equation, will I get diffusion with the right diffusion coefficient? The reason that we went through this exercise is for you to notice all the assumptions that we are making in our path to get to the diffusion equation. We're assuming surface terms are 0. We're assuming that boundaries don't matter. We're assuming that there is scale separation. We're assuming all kinds of things. We're assuming equilibration of some degrees of freedom and things like that. None of this needs to be true once you decide that you are in active matter. You're driving the system from the micro scale. There is none of the constraints of time reversal invariant microdynamics holding you back. So all kinds of crap can happen. Yes? Is it the wrong sign on the J? No. It should be against the concentration gradient, no?
It looks like a definition, like 3
I see.
things.
How about now? Slightly better? Okay. Okay. Because the flux will go against the concentration gradient. Okay. Now, okay. We're done with plain old matter, where nothing magical is happening. I know everything about Hamilton's equations and classical mechanics. I could do canonical transforms in my sleep, so I imagine that I know everything about classical mechanics. And then I built a little bit of math to go from classical mechanics to equilibrating phenomena in the particular context of diffusion. Right? Now we're going to switch. We're going to switch to the actual topic that you guys want to hear about, which is active matter. While I assure you that I will tell you fun stories and latest results and stuff like that starting tomorrow, today I'm going to beat the crap out of you by making you solve a problem, right? So let's get started on that. I'm not saying anything that you haven't already heard. This is a slide from Rodrigo's talk where he introduced the self-propelled particle as a basic model for active matter. And he mentioned the active Brownian particle and showed you the Langevin equation associated with it and the noise terms associated with it and everything, okay? Now, all we are going to do is work on this one slide for the next 15 minutes. And then we'll do some fun things. Okay, let's do the model, math of this model explicitly. I have problems here. Work with your neighbors, friends, enemies, whoever, and get started. I'm going to do some of this on the board, but I want you to get started first. Here you go. Could you pass a few back? Thank you. Actually, can you pass a few? Thank you. Just pass it around. I'm hoping that diffusion will get the sheets everywhere. But if people on the other side don't get it, let me know. Here you go. Yeah, pass it back too. A couple. This one. Yeah. Okay. Just give it a minute. If you don't get a sheet, raise your hand, and I will come drop the sheet off to you. Yes. Here you go. One moment. Here. A few more. There are a couple more here. Is it okay? Yeah, good deal. As you will see, you need what you did yesterday. Do you guys remember you calculated the expectation value of e to the I n theta? You need that answer to do this problem. The answer is there on yesterday's problem sheet if you have it. If you don't have it, I'll write it on the board. There has to be a lot less thinking and a lot more calculating for the next 10 minutes. I have written on the blackboard the one result from yesterday that you need to be able to get started on what you need to do today. Even if you did not complete the derivation of this result yesterday, don't worry about it. Just use it. Oh. Everybody look up for a moment. Is this okay? That's what I mean by n hat in that equation. It's the matrix made out of the two vectors. Okay. Do you guys know identities that tell you what cos A, cos B is in terms of other things? What you want to do as a first step is use those kinds of identities to write all of these things as e to the I sum theta of t minus theta of t prime. That's step one. Okay? Ask Wikipedia, pull up angle identities, Euler's formula, things like that, and rewrite this as an expression that only has e to the I theta of t minus theta of t prime. So this should become some matrix that has e to the I theta of t minus theta of t prime, real part, let's say. Something like that. I'm just giving you a hint so that you can do the algebra. I am writing these things from memory. I don't have the solution either, so it will be wrong. Don't believe anything that I'm writing on the board. I'm looking for you to tell me typos. Let's focus on just the XX matrix element for the next few minutes and check my algebra. And I seriously came unprepared so that I will make mistakes on the board. So you guys have to double check this. It's my way of keeping you honest. Can I ask if everybody is okay with the trig so far? Did I do it right? Okay, if I did it right, now I'm going to give you the next trick that you need. Oh, sorry, I messed up. This thing I have on this part of the board is the second trick you need to be able to do the problem, where I've assumed for a moment that t prime is greater than t. It's okay, you don't need this assumption, but let's assume that that's true. Then theta of t is the integral from 0 to t of the noise. Theta of t prime is the integral of 0 to t prime of the noise. So what you have is you have this theta of t prime can be written as theta of t plus delta theta of t prime, where this integral runs from t to t prime. This is okay? It's just simple mathematical rewriting of things. Okay, supposing this is okay, notice that it doesn't matter that this noise runs from t to t prime and this noise runs from 0 to t. It's a Gaussian process, so these things don't care about each other. That's going to be useful when you try to calculate the noise average. Okay, I'm going to let you wallow for a couple more minutes. You shouldn't be waiting for me to get anywhere. You should be driving yourself nuts, writing lots of different equations. Everybody is focusing on just the XX part of the matrix, right? This is step 1. This is step 2. And this is step 3. Tell me if you can get to step 3. I'll give you another couple of minutes before I give you the step 4. All the sweat and blood you're expending now will make all of the storytelling tomorrow a lot more fun. It's less painful when you have a friend. Okay. You guys look sufficiently miserable. Look up for a minute. Let's walk through what I did on the board for just a minute. And I'm going to actually stop doing this here. We'll continue this in the tutorial hour if you guys want to continue to work on this, okay? But let's just look at what has happened so far. This is just trig identities, right? All I'm trying to do is convert my cos thetas into e to the I thetas because I know how to do the calculation for e to the I thetas. Yes? And how to do the calculation for e to the I thetas was what we did yesterday. Then, this is just a stupid trick. This stupid trick is just saying, even though I have t prime and t, I'm doing physics. I only care about t minus t prime. Right? I should not care about t and t prime separately. And therefore, I want to rewrite this so that I can get rid of this t and t prime separately. So I have something that depends only on t and something that depends on both. This guy depends only on t and this guy depends on both. Do you see? What I've done is I've taken the 0 to t prime integral and split it into a 0 to t and a t to t prime. Thereby, I get a quantity that depends only on t and another quantity that depends only on t prime. Yes? Okay. Then I just take this expression and substitute it here using my trig identity. Is it okay? All right. Now, once I substitute it here, I have something that depends only on t and something that depends on t and t prime. Now, if I was not stupid or if I wasn't trying to torture you, I would have formulated this as 0 and t, right? So let me call this 0 and that t. Arose by any other name. Now can I do the calculation? Now do I know how to do the noise average? Thanks to what we know yesterday. This is just to torture you. The t and t prime was just put there to torture you. In general, you want the t and t prime expression because that's the most general expression you can write down. But calculating the t and t prime expression is no different from calculating the 0t expression. Right? Now you can calculate the noise average based on what you already know. Does this make sense? Then you can put it all together and you can get this fancy matrix that is there in this sheet of paper. This sheet of paper gives you the most general representation. When you want to prove it, the trick is to first set t equal to 0, t prime equal to t and change the matrix so that the expression is simpler. Then proceed with the calculation. Okay? All right. Now, stop what you're doing for the moment. You can come back and complete the calculation. Every step you need is in there. This is the only tricky step. Once you do this, everything else follows. You can do all of the other matrix elements. You can do everything, and you'll get all of the beautiful ABP results that you know. Okay? Okay. Now, let's have a little fun. Thank you for cooperating with the torture. Reward. Let's have a little fun. This is the beginning of my discussion of non-interacting ABPs. That is, I want an ideal active gas. Nobody is talking to each other. Okay? And I want to talk about an ideal active gas and talk about why ideal active gases are peculiar compared to the ideal gas we know and love. I'll tell you one story today. I will tell you 3 stories tomorrow, plus one extra fun story thrown in at the end of tomorrow's lecture. So let's start. This is just the same slide that Rodrigo showed us. There's some particle that has an arrow on it. It's moving through a medium. I have the equations of motion that you just started to torture yourself with. At short times, it moves in a straight line with velocity v0. The dynamics is ballistic. So if I calculated MSD at short times, I will get something that is t square. You saw all of this morning. And at long times, the dynamics is diffusive, and the diffusion coefficient is going to be v0 square by dr. I am staying in the limit where the translational diffusion is 0. Again, only because I want to do some math, and the math is much easier if I don't carry along the translational diffusion. Okay? So I'm going to take this model, and I notice that in the long time limit, the dynamics is purely diffusive, right? So if I have a clock that can only resolve the long time dynamics of my particle, then this system should not do anything. It should be equilibrating. right? There is no interaction among the particles. In the long time limit, the system is equilibrating. My best guess is that ideal gas thermodynamics should still hold. I have no reason at this point to suspect that ideal gas thermodynamics will be any way different for an active gas than for a passive gas, because all I have is I have to change my clock. If I change my clock, it looks diffusive, it looks equilibrating, nobody is talking to each other, so obviously this will be an ideal gas. Okay. Of course, I wouldn't be standing here and talking about it if that was the case, right? But first, let's remind ourselves how ideal gas thermodynamics came about, so that we can see why we might be wrong about our expectation that this should look just like an ideal gas. Okay. Let's remember what the pressure of an ideal gas looks like. Okay. I know the pressure of an ideal gas, it's PV is equal to NKBT. But for a moment, let's keep a mechanical picture. Because when I go to active matter, the only thing that I know that is still true is momentum is conserved. Everything else goes out the window. Energy is coming into the system at all kinds of scales, and then it's getting dissipated, and so on. So all kinds of screwy things are happening. The only thing that I know overall, that system plus environment, momentum should be conserved. So it's better to think about active matter mechanically. So I'm picking a mechanical route to illustrate my thing. But you can do this the normal thermodynamic way too. Okay. For mechanically, pressure is defined as force per unit area, right? Okay. Now, for normal matter, this is a material property. Namely that if somebody asks you what is the pressure of the gas, you're not telling them anything about the container. You just tell them PV is equal to NKBT. Measure the temperature and the volume, you know the pressure. I don't have to tell you if I put the gas in a wood box or a plastic box or what, right? But pressure is defined as force per unit area, so you're clearly measuring it at a wall. How come the wall disappears from the story? Do you see the problem that I'm trying to articulate? The way you define pressure mechanically, the way you measure pressure mechanically, is you sit at a wall and count the force. But when I state the pressure, when I get the expression for the pressure for my material, there is no information about the wall. You don't have to tell me what box you used to build the wall, what material you used. How does this magical thing come about? It comes about by the following calculation. So let's consider an ideal gas in a box. And let me define the box by some steeply repulsive potential of this form. WCA, whatever favorite potential you have that goes to infinity at very short distances and then goes to zero when you move away from that short distance. That's what my wall is going to be. I'm going to turn on WCA potentials at some length 0, at some point 0, at some point L, let's say. Then, if I wanted to compute the pressure of the gas with this wall, this, I claim, is the pressure of the gas. Let's stare at this expression for a moment and see if it makes sense. Would you agree that minus dou x, dou v by dou x is the force exerted by the wall on the particle? Minus dou v by dou x should be the force exerted by the wall on the particle. Are you guys flashing back to thermodynamics when you had work done on the system, work done by the system and all this drama? That's what we're doing now. The force exerted by the wall on the particle is minus dou x v. So the force exerted by the particle on the wall should have the opposite sign. Newton's third law never fails us. And then I just multiply it by the number of particles in my system and integrate it. That should be the force exerted by the wall on the by the gas on the wall. Do you see what I'm saying? And it's density because I divided by volume, because it's force per unit area. This is the mechanical definition of pressure. If I took the wall seriously, I put a potential for the wall, and I compute the force exerted by the gas on the wall, this would be the expression I would write down. There's no thermodynamics here. This is completely mechanics. Yes? Okay. Let's assume you guys all believe me. Now, at equilibrium, the density distribution for a given potential should be that guy, right? Boltzmann. If I give you a potential V and I ask what is the equilibrium probability distribution of the density in that potential V, it should be e to the minus V over kBt, right? Just equilibrium stat mech. Okay, so the density has to be of that form. And if I do this integral with this potential, I will get the ideal gas answer. Can you verify that? That if I do this integral with that potential, I'll get this answer. Again, you have to do some integration by parts. Even though the box, so what I'm starting with, maybe I should clarify a little bit, because you guys look more puzzled than you should be. KBT with a minus. Is this true? Is it true? No. What did I do? I just realized that this guy can be rewritten as dou x of e to the minus v of x by kbt, provided I realize that I need an extra factor of kbt and a minus sign. This thing is a total derivative. Yes? Okay. Now let's sit at the wall that's at 0 and do this integral. So this is from the wall to infinity for all I care of this. So it will be a surface integral that will get evaluated at 0 and infinity. No? So I have a wall that's at x equal to 0. This is x equal to 0, and this is where the potential goes to infinity. Yes? I should integrate it to the other wall, but for the moment I don't care. I'm just, okay, let's maybe put the size of the system here, but I don't care about that. I want to only look at one wall, the wall at which I'm doing the measurement. Now, if this is a surface term, so it will get evaluated at 0 and whatever the upper limit of this integral is, right? What is the density at 0? It's 0, right? Because the potential is infinity, the density is 0. Then you ask what happens to the density far away from the wall, because this L, whatever it is far away from the wall. I'm doing thermodynamics. I'm measuring pressure at this wall, so the system becomes far away from the wall when I go into the bulk. It should become the mean density, right? So when you do this integral, what you get is just the mean density times kBt. So this magic of the wall potential vanishing from a mechanical calculation of pressure only happens under two circumstances. You need two mathematical truths to be true. One is you need an equilibrium distribution for the density, and the second is you need this notion of far from the wall. That is, if I go sufficiently far from the wall, I'll end up in the bulk density of the gas. So these are the two things you need for the wall potential to drop out of your problem. You need that the distribution is equilibrium-like, that it's exponential and nice and pretty, and that I can go into the middle of the box and that's far from the wall. So there will only be bulk number of particles there. If I have these two statements, then the potential drops out of the problem. Now, what happens for an active gas? It turns out that in the active system, yes, the second condition is that there is some distance away from the wall where the system doesn't know there is a wall at all. It looks like a bulk system. right? So you should be able to go a distance from the wall, but not so much that you run into the other wall. You go into the bulk of the system. You're far enough away that the density has become the mean density. If you run into the other wall, then you can't do this. The potential will not vanish from the calculation. And it turns out both of these mathematical conditions that I need, one is the equilibrium distribution. There's no such thing as equilibrium in active matter. Two, far from the wall. Both of them fail for an active gas. Okay? And it turns out that by some accident of math, you still get ideal gas pressure if the wall exerts no torque on my active particle. Okay? But if the wall exerts any torque, the ideal gas equation is no longer true. You no longer get a pressure that is independent of the wall. Now, let's think about it for a moment. Let's take a classical ideal gas. Okay? No active, nothing. It's gas in this room. Let's take a classical ideal gas. You don't know if it is carbon dioxide or argon. Carbon dioxide is a dumbbell, argon is a sphere. Right? Carbon dioxide, when it has a collision with a wall, will experience a torque. It's a rod. While argon is a nice sphere. When it collides with the wall, it bounces off like a sphere. Right? In classical thermodynamics, in classical mechanics, it doesn't matter for ideal gas whether you have rods or ellipsoids. But it matters a lot if you are an active particle. If you're active, if you're an ellipsoid, you cannot eliminate the wall potential anymore. What pressure you measure will depend on the wall. So if you measure the pressure using plastic, you'll get a different answer from measuring the pressure using wood. So you cannot report pressure as a material property. You have to report what wall you used. Does this make sense, what I'm trying to say? Okay. Now I'll show you a movie. In the first half of the movie, the wall is exerting no torque. Then suddenly I turn on the torque. This is just a simulation magic. I just make my spheres into ellipsoids in the equations without changing the movie. That's no torque. And now I turn on the torque. Why didn't it play? One more time, sorry. No torque. And I turn on the torque. Okay. When there was no torque, the mechanical equilibrium for the wall was in the middle. So the pressure on this side was the same as the pressure on that side. When I turned on the torque, the pressure on one side changed from the pressure on the other side and the wall moved. Okay? What did I do to the wall? What is the nature of the wall that is allowing this transition to happen? So I'll give you a hint. One side of the wall is stiffer than the other side. Can you guess which side is the stiffer wall? I made a wall out of a material, but this guy has a different stiffness compared to this side. Which side has the stiffer wall? This side, right? The one where the pressure goes up when it starts exerting torques. Okay. Now, it turns out you can do a calculation to ask how does the pressure depend on the stiffness of the wall in the presence of torques. Okay, and this turns out to be the answer, and if you turn off the torques, it will go back to the ideal gas answer. Now, let's do a fun exercise. Find the paper. Grab a device, find the paper. That gives me this pressure expression.
Michael Cates, Aparna Baskaran.
Cates is on that paper. I can't remember who the authors were. Yes. Why are you giving people hints? Search. You found the paper. Yes, good deal. Those of you who have not seen the paper, find the paper. Don't listen to the stupid hints that these people are all throwing at you. Yes, Solon, that's the one. This paper has a laundry list of authors because the way it came about was I walked into MIT one day and said, I don't know how to calculate pressure. And then everybody calculated the pressure and told me the answer. Because I asked the question, I'm on the paper. I didn't do anything. One of my postdocs and one of Julian's students did all the work. I assume everybody found it? Okay. Now, part 2. Let's take the next 5 minutes to find two other papers that build on this idea of pressure. There is a lot known about the pressure of an ABP system at this point. There are like, I don't know, 30 papers. Find two that you like. And discuss with your neighbor and pick one of the two that you found. Give me a one-line summary of the paper. Let's see if we agree. I agree with the summary. I am the expert here. I have read all these papers and made my own version of the one-line summary. But let's try to do it. One of the critical skills that we need as scientists is to be able to quickly read a paper and decide, do I want to spend time reading this paper carefully? And the way you should do it is you should read the title, you should read the abstract, you should look at two figures and write your one-line summary of what you think the paper is doing. Then you read your summary and decide, oh no, I should understand this. And you go back and ask how they did it. That's how you read like 20 papers, 30 papers a week without actually reading the papers. I will ask, randomly pick a few people, one from each thing, and you can tell me one paper and your one-line summary. Here today. I have some more things to say, but I'll say that tomorrow.
Okay, great.
Yeah.
I don't know if you're going to mention this, but the steeper side is the one that makes the particle rotate more.
Yes.
So they go away from the particle.
No, when you rotate the torque, they become parallel. That's why it happens. Because it doesn't go all the way. Torque ends.
Yeah, just a little.
Yeah. Are we all Google scholaring or Web of Sciencing or whatever? And you also know a cheap and best way of finding the follow-up work, right? So see who cites the first paper. Do I have a volunteer with a favorite paper? Yes, go for it. Okay, bye. Tell me the other authors. He writes too many papers in this for MIPS. Solon, who else? Stenhammer. Cates, Caffrey, and Tyre. Okay. And what is your one-line summary of this paper? Okay, so surface tension of an active interface in MIPS using modified Kahn-Hilliard. Okay. I will come back and I like the one-line summary. I modified it just a little bit. I will add a couple of comments associated with this one-line summary after I get one more paper from somebody else. Go for it. Yes. Wait, let me erase the board. Don't tell me yet. Yes, what is the title of the paper?
Dependency of active pressure and equation of state on stiffness of wall.
Wait, say again, pressure?
Dependency of active pressure and equation of state on stiffness of wall.
Oh, this seems like the same calculation. Okay, who are the authors?
Ahmad Fihad.
Can I?
Yes, it's better.
Trizak? Is it Trizak? Oh, you found a paper I have not read. Super. I have never read this paper. Let's take a quick look at the paper to see what it's about. This is becoming a live demonstration of my ignorance, huh? Okay. What was your one-line summary?
He didn't get to read it.
Ah, I see. Time evolution of the normalized position of the mobile wall in simulations with 3 different combinations of wall stiffnesses. Okay. What they did was they validated the pressure expression that is there in that Solon et al. Paper. They validated the pressure expression by changing the relative stiffness on both sides and changing the density so that you're actually breaking the ideal gas approximation by allowing the particles to interact. And then they ask how valid is that expression that they wrote down in the first paper. So this is cute. I haven't read it. Nice. When is this paper from? (2024), really? No, 2021. Okay, thank you. So that's a paper that I have not read. It's in Scientific Reports. Allow particles to interact. Measure pressure. As a function of density and wall stiffness. And you guys can check if what I'm saying here is true or not, because I just spent 5 minutes looking at one figure and the abstract. I probably didn't read everything that they have to say in the paper, but this is the result that my eye picked out. It'll be fun. Check me. Come back and yell at me, saying that, oh, you should have read the paper. They said many more things. One more? Mechanical pressure. And what? And momentum conservation. Authors?
Philly, Caffrey, and Solon. Thayer, Turner.
I understood Caffrey and Solon, but I don't remember. Who was the first author?
Philly.
Philly. Oh, Yowen's paper. Okay. This Philly was my postdoc.
I'm sorry?
This fellow was my postdoc. So this is one of my postdoc's paper. I saw it in draft. I never read it. But yes. What is the one-line summary?
The equation of state is recovered if the dynamics are decoupled from the particles are decoupled from the other degrees of freedom.
Yes. So that is to say, what they showed is that if U-hat's evolution did not enter interactions, it doesn't matter what else you do to the particles, what interactions you turn on or turn off or whatever, as long as the direction of self-propulsion has boring dynamics that cannot be influenced by anything, you still get an equation of state. That's what they showed in this paper. So what I said was a little bit of a lie. It's not that all ellipsoids will have a wall-dependent pressure. It depends on which direction the self-propulsion is pointing. Okay. All right. We'll stop here. I'm sorry I went over time. I got excited by seeing a paper I have not read before. So we'll stop here. When we come back for the next lecture, it will be more of a lecture. I wouldn't make you do random things. I will tell you various stories. And there will be further Google exercises where I will ask you to look up particular pieces of information. Okay? All right, thank you.
Wonderful. Thank you very much, Aparna. So, any more questions? We did many questions during the... There is one there.
You just said that you would comment something on the first one.
Oh, yeah, sorry, I forgot about that. So what I liked very much about this paper is, wait, let me go back to my...
You can use this one.
Yeah, let's do that, because this may be too painful for me to sort out. Okay, so I just want to comment on this paper. What I illustrated in our talk was I talked about pressure as a completely mechanical quantity. What they do in this paper is there is no mechanics. They start with a Cahn-Hilliard formulation. Cahn-Hilliard formulation is basically writing down a phi to the 4th theory. So you're writing down a Ginzburg-Landau free energy to begin with. Only it's not a free energy, it's breaking detailed balance, it's not integrable, all of that nonsense. But there is no mechanics anywhere. They start high up in thermodynamics and then use that to make statements about the pressure. So it's a very nice complement to the kind of thing that we did first, the mechanical version. So this is very powerful. This paper is really nice. Yeah.
More questions? Okay, so let's thank Aparna again.